But you all came here today to hear about supermassive black holes. So let me go on to tell you a little bit about the really, really big black holes and not these wimpy stellar mass black holes. So the other main category of black holes that we know about are the supermassive black holes, which have masses that range from anywhere from millions to billions of times greater than the mass of the sun, up to billions of solar masses in a single black hole. And the first hint that monsters like that could actually exist in nature came with the discovery of quasars in the early 1960s. And a quasar is what you get when a very, very large massive black hole like that has an accretion disk around it with gas accreting or falling toward the black hole, spiraling into the black hole, and as that gas falls toward the black hole, it heats up tremendously and shines very brightly at all wavelengths across the entire electromagnetic spectrum, from radio waves to infrared light, visible light, ultraviolet light, X-rays, and even gamma rays. These are tremendously, tremendously powerful objects. And since the black holes are so massive and the amount of gas that can pile into them is so large, these are some of the most luminous objects in the entire universe. They can be seen to really tremendous distances. And the brightest quasars can actually be thousands of times more luminous than an entire galaxy full of stars. Now, these are images of quasars taken with the Hubble Space Telescope several years ago. And these images illustrate an important point, which is, and this has been found mainly from a lot of work done over the years with the Hubble Space Telescope, that quasars live in the very centers of galaxies, like our own Milky Way galaxy. Every time you look at a quasar, you see that it's in the center of a galaxy. Sometimes it's a very disturbed or interacting galaxy that's merging with another galaxy. But basically, this tells us that these supermassive black holes live in the very centers of galaxies. And the fact that these galaxies that are the hosts of quasars are often seen to be merging or disturbed tells us that there's some process involved with the very chaotic merger of two galaxies that can channel gas down to the center of the galaxies, down to where the black hole is, where it can efficiently feed the black hole. And it's thought that during these quasar episodes, the black holes can significantly increase their mass. And that's how we wind up with these extremely massive black holes that we see in some galaxies, up to billions of solar masses. Because we think now that probably all galaxies went through one or possibly several epochs or episodes of quasar activity where during galaxy mergers, going all the way back over the history of the universe, during galaxy mergers, when galaxies merge with other galaxies and become bigger galaxies, gas gets channeled down to the black hole, feeds the black hole, and the black hole gets bigger. Now, quasars are so luminous that we can see them all the way out to what is currently the observable limit of how far we can observe objects in the universe, just about. So this is a picture of one of the most distant known quasars in the universe that was discovered by a University of Arizona team using data from the Sloan Digital Sky Survey. That little faint dot right there is one of the most distant objects that we know of in the universe. We're seeing light that left that quasar 12.8 billion years ago. That is less than 1 billion years after the beginning of the universe in the Big Bang. And this is something that we want to study in a lot of detail. And one of the projects that I've worked on is using the Keck telescope to examine the spectrum of light that we see from this quasar, that is spreading the light out into its constituent wavelengths to learn about the physical conditions in this quasar. And there are a lot of important things that we can learn from this. This is from data that took several hours to obtain using the biggest telescope in the world to study this very, very faint, faraway dot in a lot of detail. And we learned some very interesting things. One thing that we learned is that the mass of the black hole in this quasar is probably in the neighborhood of about 3 billion solar masses. So this is, even very early in the history of the universe, a very, very massive and big black hole. And I'll tell you a little bit later on about how we can determine or estimate the masses of black holes in quasars a little bit later on in the talk. It has to do with the widths of the spectral lines, which come from the Doppler shifts of material orbiting around the black hole. We also see something very interesting here, which is that we see particular spectral lines that come from elements like carbon, magnesium, and iron, which we know were not present in the earliest moments of the Big Bang. Initially, the universe contained only hydrogen and helium, essentially. And all of these heavier elements had to be cooked up inside of stars and then blown out in supernova explosions. And this tells us that even basically as far back as we can currently observe, all the way back to the first billion years after the Big Bang, these quasars were objects that were located in regions of intense star formation where there were vigorous supernova explosions that were spewing out these heavy elements into the interstellar gas, and some of that gas wound up in the accretion disk fueling the quasar and building up the quasar. So even back to these earliest times, we know that these quasars were at the centers of fairly massive forming galaxies that were in the process of formation. Now, when we look at galaxies today, for example, like this giant elliptical galaxy, we think that all galaxies like this went through one or maybe multiple quasar episodes during their lifetime, and the natural conclusion is that there should be a dormant supermassive black hole in the centers of galaxies like this. We think that these dormant black holes should be in the centers of pretty much all big, massive galaxies, even our own Milky Way galaxy. But they're very, very difficult to detect. And part of the reason for that is, well, if you go back to John Mitchell's original idea of looking for material or stars that are in orbit around the black hole like that, that's very, very difficult to do because the Earth's atmosphere causes a certain amount of blurring because of turbulence in the atmosphere that makes it very difficult with telescopes on the ground to really zoom in on the innermost regions of galaxies in order to try to detect the presence of stars orbiting very tightly around the black hole. You need to zoom in very, very sharply, and ideally what you would like to see are stars that are basically doing that around the black hole. And that's not something that we can really easily do when we look at other galaxies. In fact, there's only one galaxy where it's possible sort of in real time to watch the orbits of stars around the black hole, and that's in our own galaxy, the Milky Way galaxy, since we are very close to the center of our Milky Way galaxy, if you can consider 25,000 light years to be very close in sort of cosmological terms.